Hi, welcome to SignalPad. In this episode, I have another product review for you guys. We'll be taking a look at this Tektronix RSA607A, which is a 9 kHz to 7.5 GHz real-time spectrum analyzer with a 40 MHz analysis window. It also has a built-in tracking generator that's capable of measuring return loss directly on the instrument, which is fantastic. And it works with the SignalView software platform, which became free a couple of years ago. Now, since I did my first USB spectrum analyzer review for Tech a couple of years ago, they've been hard at work and they've made quite a few new instruments based on the same platform. They even now have a network analyzer on the same form factor as this one. I'm hoping to get my hand on that and do a review on that one as well. Now, there's a lot that I want to show you about this. We're going to take it apart. We're going to take a close look exactly what's going on inside and a whole bunch of different instruments to take a look at its capabilities, some of its weaknesses, and see if it fits your application. So let's get started. So we can look at the line of USB-based instruments that Tektronix has to offer. And if you look here, there's a couple of them listed here. Now, when I reviewed the RSA306A, when it first came out, I was really impressed with the fact that they made this SignalView software completely free, and it's still free, of course. It has 17 different measurements that are included in it by default, and some of the other advanced measurements like demodulation and as well as compliance and so on, obviously you're going to have to pay for, but they've reduced the prices of those significantly as well. And all of these instruments work with SignalView, and this software runs across all of their spectrum analyzers, making a cohesive, unified platform that you can simply jump between very quickly. I had no idea that they were going to go ahead and develop so many USB-based instruments. Now they even have a network analyzer, which is in the same form factor. So it's really good to see that. So we're looking at the RSA600 here. And if you look at that, and the RSA500 and 600 are essentially the same thing, except one is battery powered. Now, in this particular unit, you can go all the way up to 7.5 GHz, starting from 9 kHz. And we have a 40 MHz capture and analysis bandwidth. Now, the price is between 6,000 to 10,000. And it's a great price. It is extremely competitive, even to companies like Rygo. If you look at the Rygo's spectrum analyzer, the DSA857TG, which has essentially the same spec, 7.5 GHz maximum frequency, but it has no real-time capability, and it doesn't have the SignalView software that couples to it, and it's the same price. So they were really going after the market, and I don't think there's anything like this on the market right now with these capabilities at this price point, given that you can always expand its capabilities through SignalView with additional compliance and demodulation capabilities and so on. So it's really impressive, and it's a great sign for the industry and for everybody who's buying these things, because it just means they're going to get cheaper, they're going to get more capable, and Tech is serious about these units, and they want to basically capture this market, and I think they're doing a great job with it. So now that we have an idea of kind of what's going on and what the offering is, now we can go ahead and actually take a look. First of all, I want to take it apart. I want to show you what's inside of it, how it's built, what does it look like, how does it compare to the battery powered version of the same instrument, and then we're going to do all of our experiments with it. So I'm really excited to get started. So let's take a look at the front of this unit. Here we have obviously the USB 3.0 connector with a screw-in terminal. It comes with a special cable that ties into this and protects it from getting yanked out or bent or broken. This is particularly useful for the version of this unit that is battery powered for outdoor use, and this would be pretty handy as you're moving around. You want to make sure it doesn't get pulled out or damaged. So we also have the power LED and activity LED, antenna in for GPS, of course. We have the RF out for the tracking generator, as well as the reflected wave going back in. And this means that you can do your return loss measurement without the use of an external directional coupler, which is a huge advantage. So, and we'll talk about that, I'll do measurement on this. There is the reference input for 10 MHz triggering, so you can trigger on a particular digital activity through the SignalView software, of course, and the RF in, which can take 40 volts as well as 33 dBm, so 3 dBm more than typically you would see on a spectrum analyzer, which is pretty handy, especially when you're outside and trying to connect to some unknown signal. So pretty nice, pretty straightforward. Now you may ask, why is this in the front? It would be for a benchtop instrument like this. I would prefer to have this in the back, of course, because there's no reason for it to come out. For an outdoor unit, battery powered, I can understand. But once I take it apart and take a look inside, as well as looking at the architecture, it will become clear why they had to put it in the front of the unit, and also because the battery powered version has to have it in the front. So yeah, it looks good. Let's take a look at the back of the unit. And at the back of the unit, pretty straightforward. We have the AC line going in, we have the fan, of course, and we have the 28-volt noise source control for the output at the back. Now, I could not find a way to activate this 28-volt source through the SignalView software. It's probably a feature that hasn't been implemented yet, or if it is somewhere in SignalView, it is really buried into all the settings because I could not find it. Now this would be obviously used for measuring noise with an external noise source, and I would love to do that, and I wanted to show it on camera, but I couldn't find a way to access that. So it's probably not implemented yet, but it's good to know that it is there, meaning that eventually this instrument will be easily retrofitted to be able to do noise figure measurements. Alright, let's take a look inside this unit. I've already taken the top off, and take a look how nice and clean the design of this unit actually is. It's also really modular, and that modular design makes sense to me because, as I showed earlier, there's a version of this instrument that has a battery powered basically, and it has the same RF specification as this one, so it would make sense to use the same RF deck and the same digital deck and share it between those two designs to reduce the cost of development. And at least this is what I think is going on over here. And as you can see, they've pushed out the design of the power supply, the fan, the AC line coming in, and the 28 volt for the noise source completely outside of this because it's not shared with the other instrument. And the design is really simple. The power management of this board requires only 3 wires and perfect for battery powered application. Now on this power supply, which is from XP Power, it says output 1 is at 12 volts. Now there's 3 wires here, so I suspect there is an output 2, perhaps 5 volts, but I'm a little bit surprised that it's not listed here. Either way, the simplicity of this is really in line with having a battery powered instrument. This line over here is nothing more than the 28 volt control to turn on and off the 28 volt noise source, and there's a DC-DC converter on this board over here because this guy doesn't generate 24 volts, so obviously you're going to have to step that up. And interesting also to see that the fan control directly comes from this board, and just for simplicity they have basically put that design onto this board as well. Again, I think this is unique only to this instrument, not to the battery powered version of this. AC line is all good, everything is tied down very nicely on this board as well. Mechanically it's nice and solid. There's nothing unusual going on over here. There's a couple of connectors over here that are not used. I wonder if they're used. This looks like more of a power connector, perhaps for the battery pack, for battery balancing maybe. I'm not sure, but there's a bunch of stuff that's not used, which may be indicative that this is the same design used in 2 places. There's also some connectors over here which we'll take a look at for programming and configuration. Perhaps there's a button over here, interestingly, and I will take a look at that as well. But other than that, really pretty straightforward. Now, there's one other thing I wanted to mention here is that you could potentially, if you really wanted to, figure out a way to retrofit this with a battery yourself. Now, obviously, the warranty and stuff would be out the door, but there's nothing stopping you from trying to do that, given how simple the design of this particular power system is from this point of view. Now, there's a lot of empty spaces in here. You may ask, well, why all the empty space? Well, because they want to make likely they want to make the length of this device to be compatible with benchtop instruments, and this stacks quite nicely on top of, let's say, Keithley source meters and other multimeters and so on. So I think this is for consistently with those, and otherwise it's quite nice. No complaints there, but we gotta go a step deeper. And here's where all the magic happens. I've taken the board out, and it's just so nice. Always such a pleasure looking at well-designed and mechanically engineered instruments there. So obviously this is all enclosed for various reasons, as well as isolation, protection, heat sinking. There's a lot of reasons why they do this. So let's go ahead and take the top off, and let's see what's on the board and also the bottom, so we can take a look. There is a sticker here for warranty, so I'm going to take that off. I think it's well worth taking a look to see what's inside this. So here are the top and bottom plates of the RF and digital deck, and look how beautiful they are. Obviously you've seen these before in many of the teardowns that I've done in the past. You can see conductive sections that touch onto the PCB and create a nice shield there. Each individual segment is typically for a separate function so that they don't interfere with each other. Various filters and synthesizers and so on will be in different sections, as well as the digital blocks. Several pedestals you can see in a couple of locations. On top of them there's thermal putty. Those touch some of the higher power components there so that they can take the heat out of the unit, so that the unit doesn't obviously burn up, and improves the age of the components. Couple of places over here you can see we have absorbers on some of the critical places. For example, at the input RF section we have absorbers, and some of the synthesizer sections in the corner we have absorbers to make sure that, first of all, we don't build a resonant cavity inside this, as well as we don't get multiple reflections building up. You get a standing wave inside the cavity, which you don't want, of course. And yeah, so other than that, looks pretty nice and straightforward, very clean. So let's go and take a look at the board itself.
And here is the RF board and the digital board as well. And it looks so beautiful. So let's take a look at some of the components. I'm not going to go into too much detail there because I've talked a lot about these different components, but it's still interesting to kind of see the signal flow here and see what happens to the various components. Here's our tracking generator output. Here's our RF input. So naturally, we have an AC coupling, which is the very first thing this port sees, as well as a whole bunch of switches that switch to different bands. We've seen these solid-state switches and attenuators being used in the front end, first to switch attenuation, as well as to switch to different bands, and these bands then separate the frequency into multiple sections processed by different mixers and different filters. And this is critical to get good harmonic rejection and harmonic behavior from the whole instrument. So here you can see, for example, one path here and one path here. Then on this path, we see a whole bunch of microwave filters. Again, we have some conical filters, some LC stop filters over there going into a mini circuits double balanced mixer there, and we have these three components here. These are hybrid microwave filters, and I exactly don't know what the part numbers are because I don't want to take these covers off. That it would be hard to put these back, but these are typically hybrid modules. You can buy them and they come in a separate solderable reflow package there, and inside the package there's a cage, as well as you could even use other fancy materials. Some of them can use ceramics for very high quality filters if you need to. This could be SAW filters or who knows what they are, but either way it's clear that they are filtering the signal in multiple stages there. There's another double balanced mixer here. Here's yet again another mixer there. Here's another SAW filter. You can see there's a couple of these also on this board. Now this board has tons of synthesizers on it. I mean, there are synthesizers here, there's a whole bunch on the other side, and there's another synthesizer, there's another step attenuator here. This obviously step attenuator controls the power coming out of the tracking generator. There's a multi port switch, RF switch here, getting signal from a couple of different places before sending it out, likely because there are different synthesizers covering the full band. So this is how they probably select that. Whole bunch of microstrip hairpin filters here. Again, you can see switches that select between which filter has been used, separating the band that is being processed by various different kinds of filters. So really quite beautiful on this side. Now, if I flip it to the other side, you will see a whole bunch of other components. Again, on this side, we see a few other interesting things. Now, this is the GPS antenna, so therefore, clearly, this is our GPS module. A whole bunch of DC-DC converter sections over here, a Spartan 6 FPGA. This IC here is directly connected to the USB 3. It's a little hard to see the part number, but I suspect that it has to do with the USB 3 management device there, and this is one of the ones that's heat-synced. So there's a lot of data going through this IC because this is constantly working when it's running. As a few more filters and another one over there. Here's a VCXO, high-quality VCO there. A linear device, there's a synthesizer, yet again another synthesizer there. There's just so many synthesizers all around. Here's our ADC. This is a 12-bit up to 105 megasample per second, I believe, ADC. I think this is from Linear Technology as well, if I remember correctly. Yep, I think it is. So it is a 12-bit A to D converter there, which again makes sense. And you can see the IF paths coming in from different locations and then going into the ADC. Very classic architecture. Obviously, the devil is in the details, but you can clearly see what they're doing. Another interesting thing I came across here is that this section over here, this IC over here is a linear technology battery management IC and charging IC. So I was definitely right about the fact that this connector is for the battery. And it's interesting that this part is conformally coded and the other side as well, but not everything else. And I suspect this probably has to do with the fact that this is dealing with a battery and they want to make sure that it is perfectly covered and protected. And they obviously you don't want to put conformal coding all over your RF sections. It would be quite bad for it. But depending on the dielectric properties of the conformal coding, but I suspect it's never optimized really for RF performance. So you definitely don't want to do that. But this section dealing with the battery, being critically sensitive to moisture and actually being dangerous in case that something goes to the battery, perhaps this is the reason why it's conformally coded. There's fuse in there as well. Another mixer over there. And I was saying there's another synthesizer over here. It's just full of different sections. Really beautiful, very nice design. Again, to be expected, they have really perfected the design of this. Now, if you look very carefully, you can see the footprint strategy makes sense as well. So there's a line over here. Everything on this side is RF, and everything on this side has the digital parts in it. So you process the RF here, you generate your synthesizer here, you do down conversion, you do filtering, everything over here, and then ends up at this side of the IF, going into the ADC, going into the FPGA. So this section is all digital. Battery management section, GPS receiver, USB communication, Spartan FPGA, IF processing and digitization, very separate from the whole section that does the main RF down conversion. All that makes sense. This is obviously you want to do that, and it sounds really simple when you look at it from this point of view, but imagine you have all these components you need to lay this board out. There's a lot of trade-offs you need to make sure these things actually line up, and how you strategize to make sure the signal flow actually flows in this direction. Look up, this is exactly the flow of the signal coming in and going out. So there's a lot of thought that's gone into this. Really beautiful component placement, high quality. There's tons and tons of components from basically the best vendors in the industry for ASIC for these components, and they've used them all. So yeah, no complaint really about this. Now you have to look at its performance, but I would say from the experience they have gathered making other USB spectrum analyzers to this point, this is going to perform quite nicely. So I'm eager to put it back together, get on the bench and do some experiments with it. So there was one other little thing I forgot to mention while I had it open. These coaxial connectors are actually spread throughout the entire board, allowing the technician or whoever is testing the board to be able to monitor various signals across the entire RF deck. And here on the outside there are two of them, and in between there is a coplanar waveguide, and it looks like that they're using this to characterize the board perhaps afterwards to make sure to see what the losses are. There you can see how the solder mask is taken away from the coplanar waveguide section there to improve its RF performance. So there's a little tiny test structure on this board allowing them to characterize it. It kind of looks cool. Now let's see if we can use this instrument to reverse engineer an RF transmitter that we don't know much about. This particular module here is from a drone remote control. Now this is a very simple one, doesn't really have much stuff on it, but you can see the two actuators used to control the drone's location, as well as some LCD screen for feedback, some buttons and so on. There's really not much going on here. This is a fairly simple one, doesn't have that many channels, but we don't know anything about it. I don't know what the carrier frequency is, I don't know what modulation format it uses, or how it encodes the data when it's transmitting it. I want to see if I can use this instrument to figure all this out. Now let's take a close look at this here. So on the other side, we will have a couple of components. So we have this Hitachi component here, which just controls the LCD screen. Nothing that interesting there. And there is a component whose numbers have been rubbed off, and that most likely is a microcontroller handling the switches and reading data from the potentiometers on the little actuators, and then digitizing them and sending them to the RF transmitter module. And they have gone through the trouble and actually spray painting the back of the RF module, which I feel kind of is unnecessary. I mean, first of all, paint comes off, and really, do you really need to do this on something so inexpensive? But anyway, so let's go ahead and see if we can figure out how exactly it works. In the place where there used to be an antenna, I have soldered an SMA cable, so we can connect the SMA cable directly to the input of the spectrum analyzer, and we don't have to do measurements over the air, which would be quite unreliable and difficult to do, not just because of multipath and attenuation and so on, but because this may be operating near ISM bands, and there's a whole bunch of traffic here in the lab from routers and Zigbee switches and a whole bunch of other things, and we will interfere with this. So let's go ahead and turn it on. So I'm going to connect it directly to my Keithley 2280S power supply. This is a really nice power supply. I've been using it a lot lately. High precision, very fast reading. It's 6.5 digit monitoring there. So I've already set it to 6 volts, 0.1 amp. Let's go ahead and turn it on. And let's go down here and see what it looks like. And there it is. You can see that it's powered on. And at the beginning, a lot of these drone remote controls need you to actuate the up and down a couple of times before it comes online. So we're going to go down, up, and down, and now it's green. And it used to actually have a buzzer here that I removed because it was ridiculously loud. So now you can see on channel 1 it's connected to the up and down position of this particular control there. You can see it goes from 0 to 100%, and if I push it left and right, you can see the channel will change, and now a different channel will show me numbers. So you can see the different channels that are active. So here's channel 3 up and down, and then there's channel 4 left and right. So, and there's a whole bunch of buttons for calibrating the locations, you know, the 0 default location. So it's obviously sending some data out. Now let's go connect it to the spectrum analyzer and see if we can figure out exactly how it works, which would be pretty interesting. All right, here is our setup, very straightforward. The antenna directly connected to the input of the spectrum analyzer, nothing fancy going on. Now we can go ahead, turn it on, and let's go to the PC and see what we can find out.
All right, so let's go and try and find our signal. Now the easiest way to find it is obviously to look at the entire span of the spectrum analyzer. So let's go ahead and click that. And now we're going from 9 kHz to 7.5 GHz. and we should be able to occasionally catch some of these signals. And there you go, we just caught one over there, and if we wait long enough we will see another one. There's some more here, and you can see that there's a whole bunch of activity here that are happening around this ISM band of 2.4 gigahertz. Now you're not going to catch every time there's activity, because this is sweeping very slowly, and you're going to miss a lot of these tones that are coming out. Here's a full one actually, caught the entire packet, so we see the whole power. And sometimes we will see some tones appearing out here, which are the harmonics of the main tone coming out. That's not a very good transmitter. You shouldn't really put out tones outside the frequency you're supposed to be operating there, but anyway, this is a pretty inexpensive component. So now that we know that signal is present around this, there you go, there's the harmonic I was talking about. So now that we know that these signals are here, we should be able to zoom into there and take a closer look. So let's go to the 2.4 gigahertz band there, and we're going to change our span to 40 megahertz. So there it is. We can see a whole bunch of activity, and now we can go ahead and create another trace. Let's say trace number 2, and in this trace we're going to do a max hold, and we're going to show that trace, and you're going to see a whole bunch of activity being recorded. Eventually you'll see the envelope of the signal. There's a couple of things to note here. Even though there are distinct tones that appear, there's a whole bunch of other power. You know, look at this big amounts of power coming out. Some of this is because it's just a bad transmitter. Some of it could be pilot tones and preamble tones and other things coming out. You also notice that it goes beyond the 40 megahertz analysis window, so it goes beyond the 2.42 gigahertz there. So I can shift the frequency higher so we can see more tones. So instead of 2.4, let's say we can go to 2.45, another 50 megahertz up, and you can see some more activity again. So 40 megahertz is definitely not enough to see all the frequency content this transmitter is putting out at once. You can see individual tones, but not all of it. Now it would be great if this had, instead of a 40 megahertz bandwidth, let's say 110 megahertz bandwidth. But the challenge with that is that on a USB instrument like this one, if you were to increase the span from 40 to 110, aside from all the hardware difficulties from the RF portion itself, you're going to have to send a lot more data to the PC. So maybe next generations of these instruments, when there is USB-C and Thunderbolt and so on, they would be able to have higher analysis bandwidth. But 40 megahertz is plenty, and there's a lot you can do with just 40 megahertz, as you will see. So now we can see that some of these tones, the power is quite a bit large, larger than the 0 dBm here. So let's go and change our reference level from 0 dBm to, let's say, 6 dBm. So now we won't saturate the input. So there you go, looks good. So this is a nice place for us to start. So let's go ahead and add a DPX window. Now here, this is going to be the real-time DPX analysis. Now we're going to be able to see much better what's going on. Now my computer is actually quite slow here. So here we go, and there it is, and check it out. I mean, it's just a jungle out there. It's jumping all over the place. There's a lot of other tones that come and go, even though it looks like that these tones are on at the same time, but that's just a residue from the DPX's window that I can change the time constant of these displayed waveforms there. It's about 10 to 100,000 spectrums per second, but there's only one on at a time. And by looking at this, you would immediately recognize that this is a spread spectrum communication system. It's a frequency hopping. And the way these frequency hopping spread spectrum systems work, I've talked about this before. Sometimes they follow a predetermined sequence of channels. Sometimes it's random. Sometimes it is encrypted. But sometimes they send a preamble so that the receiver can log to the channel. So they kind of prep the receiver, say, I'm going to be transmitting at this frequency. The receiver catches that, locks onto it, and then the packet of data actually comes following it. So we can find out exactly what it's doing by taking a closer look at these pulses as they come out. Let me go ahead and turn this trace off. So right now the way it is really difficult to use because we have no trigger reference. So we can go ahead and define a trigger reference so we can make a measurement with respect to a repeated event. So that's pretty easy to do. Let's go and add a couple of other windows there. Let's add a time overview window and a spectrogram window. And now we go. We're going to get a bunch more. Now it's going to take a bit of time. Again, my computer is not very fast. Here, there it is. So you can see that occasionally on this time overview, you can see these pulses come and go. But we're looking at only a 7.4 microsecond duration. So obviously we're not going to capture everything. But as you can see here, when it's sending data that I'm interested in, it exceeds about minus 3 dBm of power. It goes even above 0 dBm. But minus 3 dBm seems to be a good reference point for us to use for triggering. And this instrument obviously supports triggering. So let's go ahead and define our trigger. So we can do it either on the falling edge or on the rising edge of the signal. Now, generally when packets are sent, it may be that they have a slow start and they may have a preamble or a pilot at the beginning, so it might be difficult to trigger on that. But once the packet is done, they collapse the output power. So we can use a falling edge in this case, and let's set the level to, let's say, -3 dBm. And we can go ahead and enable the triggering from free run, and there it is. Look at that, we're catching the falling edge of an individual packet. Now we're looking at, again, at a very small window. We can change that. Let's go ahead and look at 500 microseconds, like that. And here we are. We can see we are triggering right over here, and we're catching one of these packets, but it doesn't seem like we're looking at a long enough duration. I want to see more than one packet so I can get some information from that. So let's look at 1 millisecond. So here's 1 millisecond, and there it is. Look, we are actually able to catch 2 packets. Now this is trigger point is on the falling edge, so let's move the trigger point to the left. Let's go all the way to, let's see, it's not the fastest computer in the world. Where can I go? Let's say, I think probably about maybe 200 and 250 microsecond would probably be a good spot. There you go. You can see it's moving into the center. I'm recording the screen here as well as a bunch of other things, so it's not the nicest PC at the moment. There we go. Maybe 250 would probably be a good place to stop. And there it is. There we go. Check it out. Now we can see exactly the activity that we're interested in following. Now, there's a lot we can look at this. So let's pause it for a second. So, and take a look. So we have 4 windows here. One is our spectrum, and this orange line is the instance of the spectrum versus time that we're looking at a particular time. I'll show you what that means in a second. Here's a DPX. There's a bunch of activity going on. Here's the overview of versus time, and here's our spectrogram. So let's put a marker on this. Now, all of these markers on all of these screens, as well as the plots, are time correlated. And this is why it's so useful to have this software coupled with this instrument. As I've said before, if you're going to make a USB-based instrument, or any instrument, if your software isn't great, then you can have the best hardware in the world and it wouldn't matter. So here, this time correlated measurement is extremely helpful. So you can see on the spectrogram some activity shows up as hot, it means power is coming out. And this activity here, you can see that's that pulse right there. And if I follow that, go to the next one, that's this pulse over here. And then the other pulse is outside of the screen. So when I'm here, I can clearly see that there's 2 pulses in a row, and they're quite a bit different from each other, even though they look very similar. And the difference is that the duration of this first pulse is quite different than the other one. So this is a much shorter pulse than that. So what could that possibly mean? Well, it could be that the transmitter, first of all, sends a small amount of power here. This could be for alignment, for frequency detection from the receiver. I'm not quite sure why it's doing that. It doesn't seem to be high enough to do that, but anyway, it's sending the CW tone at the beginning. And then it ramps up the power, and then it keeps the power steady, so it's doing something during this portion, and then drops the power, waits for some time, and does it exactly the same thing again, but this time longer. Now, it could be that during this packet of data, it's sending its ID, so that the receiver knows that the transmitter is talking to it and not some other receiver sitting on the same channel. So that, for example, is one possibility. And then it sends a longer packet, so that perhaps the receiver say, okay, now this packet is mine, the one that actually considered this to be aimed at that particular receiver. So we are interested in looking at both of these, but it's likely that the longer packet is the one that contains the data related to the states of the actuators and buttons of the transmitter itself. So it will be better to look at this one. We can look at both of them, but it would be better to look at this one and figure out what's going on. Now, given that the amplitude is so constant, it is possible that this is, for example, an FSK system, a frequency shift keying system. So we should be able to look at frequency versus time during these packets in order to make sure that this is indeed sending data during that time. Now, as I was also mentioning, if I go over here during this packet, I can actually clearly see the spectrum, and I can see how the spectrum evolves between the packets. There's nothing, and I go back up. I get my spectrum back, and then next packet, and so on. So it's very clear what is happening in these spectrums by having these windows at the same time. So let's go ahead and run this again. And you can see that sometimes the distance between these pulses changes. It's actually a little bit misleading. The reason this happens is because on the falling trigger point, sometimes it triggers on the longer packet than the shorter packet, you can see. So that's why it shifts around. This is a common problem. Now, normally, you would want a more advanced trigger menu, but this doesn't give you dwell time, for example. It doesn't tell you hold off, doesn't give you any of those abilities that, at least that I can find. And the biggest limitations of this is the fact that the trigger bandwidth is not changeable. So this, I'm not sure how difficult it is to do this in software and if they can be implemented later, but it doesn't matter what bandwidth you're looking at. It will always trigger at 40 megahertz. But if I want to keep this spectrum steady, it means that I'm only interested in looking at, let's say, one channel only. So I can center the screen, so I can say, go to the center frequency of 2.465, let's say, gigahertz. And in the center, that's one of the channels. You can see it sometimes shows up here. So what if I want to only trigger if the signal is on this channel? And I could do that potentially by reducing the span just around this tone so that it doesn't see the tone that, for example, shows up here. But unfortunately, it will still trigger even if I'm not looking at it outside of this window. So this is something that limits you and makes it a little bit difficult to look at this data, especially for a frequency hopping system like this one. You can, of course, pause it, stop it, and then replay the ones that you want to look at. But then doing a live measurement becomes more difficult. So let's go ahead and try and see if we can look at this. So we're going to have to add another window for this. So we're going to go ahead and add a frequency versus time window because we think that this is an FSK system. So let's go ahead and add that. And there is our window. So now we have all of our information that we would need to decode this instrument. This is a mysterious transmitter here. So this packet here is obviously correlated to this portion. And this packet over here is correlated to this portion. You can see how it's jumping around, and you can see how the center frequency of the packet changes. That's because it's jumping channels. So you can see this is one channel, sometimes it catches this channel, sometimes it catches the other channel, and this is where the trigger would be so useful. I could tell it only trigger when you're on this channel, but unfortunately I can't do that. So it's going to be a little bit difficult. So now I want to zoom into here and figure it out a little bit more. So let's pause this for a second so I can zoom in. And the zooming on this is not the friendliest thing. So you can zoom, you can't just draw a rectangle and zoom, which is the one that most people are used to. You have to zoom in horizontally like this and then vertically like this, which is a little bit tricky, but there we go. And then you can span it. And there are bits. Look at it. It's like a magic thing. You can clearly see the bits here. So I can move my marker over here, there. Now you can see my marker, individual bits as a function of time, showing the frequency deviation, looking at the spectrogram, and looking at the spectrum at the same time. It's wonderful. I mean, this is what you want from an instrument, really giving you every piece of information at once. There it is. So now we can see it. Now it's fairly noisy. Let me run it. So you can see that it sometimes goes away outside of the screen, and that's because it's not always catching the same window. But anyway, there's nothing I can do about that. Unfortunately, at least I couldn't figure out a way to get this to stay steady here. So let me try a slightly different frequency. 2.456 gigahertz. Let me see what happens if I put it. You can see now it's catching the other channel first. Yeah, it's not exactly what I want, but it's close enough for our purposes. So there is our 2.465 gigahertz. So there's our center frequency. It's going to show up there. There it is. So this is the one we want. So let me pause it, and I can go ahead under View, and I can go under Replay toolbar, and it has everything that it has saved. I can go ahead and replay. So I can go back, and there it is. So we have now one packet. Now take a look at this. As I said, it's noisy because we're looking at a very large bandwidth, but I can change that. So I can go over here and I can go under its settings, and I can say do not link the analysis to the span. Look at a smaller window. Look at a 10 megahertz window, for example. So now if I run it again, next time I catch a sequence, it's going to be, if I press enter, of course, it's going to be much cleaner. If I can catch one, that is. Let's see, where did it go? I lost it. Did I lose it? Alright, I found a somewhat acceptable solution. And what I did is that I changed my sender frequency to 2.385 gigahertz. And our analysis is now done around that center frequency. Now it happens that only one channel from our spectrum transmitter falls within that bandwidth. As a result of that, the trigger can only happen on that one channel because the other ones are just simply outside of the measurement bandwidth. We won't be able to see the other channels anymore, but this should be good enough because these are all the same data that comes out of the channels. It's just jumping around. There's one way to work around it, but unfortunately now you're going to be missing any of the spectrum outside. So if there's an issue with them, you won't be able to detect it in this condition. But good enough for our purposes. We still have the issue that the trigger sometimes triggers on the long pulse as opposed to the short pulse, and that's why it's jumping around still. And that needs a dwell time or a hold off time in the trigger menu to resolve that. And I really hope that these two changes would be implemented, because they would be an enormous advantage to be able to have these, because as you can see, the limitations of not having these two trigger functionalities make the measurement quite a bit more difficult. Now let's look at this. Now obviously we can see the bits, but it's not very clear, and that's because we're looking at a 40 megahertz bandwidth to do this measurement. And that's not really a good idea, because these are much smaller channels. No reason to try and do FSK computation on an entire 40 megahertz channel. It's going to eat into your dynamic range. And they've thought about this, and you can actually change that setting. So it says link to span. I can remove the measurement bandwidth so that it's not linked to the span. If I remove that, and I can change that, let's say I'm going to look at only a 5 megahertz bandwidth. But as soon as I do that, I'm going to lose my measurement, because by default this 5 megahertz analysis is done at the center frequency of 2.385 gigahertz. But that's not what our channel is. Our channel is all the way out here. So we're going to be missing the data completely because we're looking at this area. Well, they thought about that as well, and we can make that change too. So here there's another button that locks the center frequency to the measurement frequency. Now we don't want that. We're going to remove that. And we're going to say, well, our measurement frequency is around over here, so I can actually move this manually myself and put it right where I want it to be, which is somewhere around here. That should be it. There we go. So now we have our measurement around that frequency. Now we don't see anything again. Unfortunately, I'm going to have to auto scale this, and there it is. Now we see it again, and I have to zoom into this again. Let me zoom in and come back. I'm sure you don't enjoy me zooming through this neither. And here we are. Check it out. The bits are very nice and clean. You can clearly see individual bits and transitions between them. And so now let's take a look and see if there is any correlation between these bits and the settings on the controller itself. So I can go ahead and change one of the actuators. I can, for example, push the forward and backward movement and see if any of these bits change. So have your eye on it, and forward, and check it out right in the middle, and backwards. You can clearly see how it's counting. So it's converting that voltage to digital, the potentiometer, and then sending that through this particular set of bits through this packet of data. So this packet of data is partially, you can see this section of it is responsible for that potentiometer. What about another one? Let's go to the other side of the controller. I'm going to push it forward and check it out right over here. These bits, I can go the other way. These bits are responsible for the other side, the other actuator. And if I go left and right, here's left. Take a look over here in the center, to the right. There it is. So each section of this bit sequence is dedicated for the setting and the status of one of these individual potentiometers. And if I push a button, let's say, I'm going to repeatedly push this button. Check it out right here. This bit, every time that bit is there, it means the button was pressed. You see that? There it is. Yeah, it basically, this is what you need to do to reverse engineer it. And you can now correlate each of the bit sequences to a particular component on this board, and then you can find out what message is being sent, what the sequence is, how the bits are converted to digital, and it's all in there. If I go over here and look at this sequence here, I will be able to see the channel ID that's being sent, which has nothing to do with the settings of the controller. So all of this is possible because of doing this real-time measurement and being able to do frequency versus time and amplitude versus time, if this was an ASK system, for example, and showing it all at once and have a clear indication of exactly what's going on in the transmitter. Just think about where we started from. We started from some random spikes on a spectrum analyzer that we would occasionally catch every once in a while to be able to completely decode the message that's being sent by the transmitter, all in one software and in one instrument, without having to do anything else. So I'm really happy with the performance of this, and it continues to grow and continues to get better, of course. But this trigger limitation, it makes it a little bit more difficult to do some of this, but easily fixable, I think, and then it would become even more powerful and more capable.
Alright, now for our next experiment, I want to measure this mysterious component. And this component has TX and RX written on it. And on the other side, it has an antenna port. So this is clearly either a diplexer or a duplexer, except that we don't know which one it is. And we want to measure it and find out using the RSA607A's built-in tracking generator capability. Now with the tracking generator, we can send signals to various ports and see what the exact frequency response of this instrument is, and from that we can make some conclusions. Now to start, I'm put a through between the two ports, and this allows us to calibrate the instrument first for zero reference power, and then from then we can go ahead and measure this. Now before I do that, I want to show you a couple of settings that we can do on the signal view software to configure the tracking generator itself, along with a couple of different limitations that I hope they can remove in the future.
Okay, let's go and configure the software to do this measurement. So first off, we're looking at the spectrum. We don't really need that, so let's get the right window in here. Under the tracking generator, I'm going to get the transmission gain window, get rid of the spectrum window here. And this window is going to now give us the ability to configure the tracking generator, the frequency, range, and so on. So right now it's going from 980 megahertz to 1 gigahertz. That's obviously very small. So let's go from 1.5 gig all the way to, let's say, 3.5 gigahertz. And let's change the resolution bandwidth to 1 kilohertz so we can get a little bit more dynamic range and a number of points to 200. So now we're going to see this march along the way. Now, this is not as fast as I would have liked it to be. This instrument is not optimized for sweeping speed along very large frequency ranges. So it can be a bit frustrating if you have to do a live measurement and keep seeing the result as you're changing something, like if you're tuning a filter. But you can always change the number of points, the resolution bandwidth, depending on your needs. And for most of the time, it would be okay. So now let's go under tracking generator menu and increase the power here. Now the highest power this thing supports is -3 dBm. Again, this is okay for most things, but if you have a very high loss system you're trying to measure, it's going to eat into your dynamic range again. So you have to just make sure that this is sufficient for your needs. For active circuits, obviously it's more than enough, but for passive circuits, it might be just a little too low. But again, depends on your needs, and most of the time it will be fine. So now that we are set this up like this, we can see that even without normalization, we're doing pretty well. This thing has a very accurate output power control right off the factory without needing for any normalization. But nonetheless, I have a through, so we can do normalize this circuit. And it gives you the temperature and the settings that you're doing it and so on. So we can just bypass that and perform a normalization. It also gives you a couple of hints on how to improve your normalization performance, and then later on the measurements you're intending to do. Now during the normalization, it will apply a signal through the RF port and then look at it through the RF in port, get rid of the losses of the cables in between, and make sure that you have a very flat frequency response, adjust your reference, and make everything ready for you to be able to do the measurement that you want to perform. Now it's almost finished, and there we go, and we're done with that. So now we can see very nice flat line from 1.5 gigahertz to 3.5 gigahertz, 200 points, 1 kilohertz resolution bandwidth. So it looks good. So let's go ahead and actually change our setup so we can find out what kind of device we're looking at.
Here we go. I've removed the through line, and I'm connecting the tracking generator directly to the TX port, and the antenna port is then connected to the RF input, and at the same time the RX port is terminated. This allows me to measure the frequency response from the tracking generator to the antenna.
Alright, now that the setup is complete, let's run this again. And you can see that we obviously have no transmission at this frequency. It's going up, and there is our channel. Look at that, very nice. You can see clearly that from the TX port to the antenna, we indeed have a bandpass response and fairly high quality factor response. And then we can see that it has very nice transmission, almost 0 dB of insertion loss at that point. Very good, let's put a marker on this. There we go. So our forward transmit channel is sitting at 2.465 gigahertz. So it looks very good. Now what we need to do, we need to change the setup to see what the response is from the receive to the antenna, or I should say from the antenna to the receive. So we have to rewire it. But before we do that, let's go under traces and let's freeze this trace so that it doesn't change while we're doing our next measurement, as well as the fact that we can enable trace 2. Now trace 2 is still measuring the old configuration, so it's going to basically overlap this measurement. But no worries, after it's done, I'm going to just pause it. So when it's completely finished, it's going to stop, and then we're going to change the setup and do the measurement again.
And here I have changed the setup to do the opposite measurement. Here I have the tracking generator connected to the antenna port and the RF input connected to the receive port, with the TX being terminated. So this now allows me to measure the frequency response from the antenna port to the RX port.
Alright, the setup's changed. Let's run this again. And now it's going to do the same measurement, and let's see what the RX response is. And check it out, it's a different frequency. So this is indeed not a duplexer, but it's a diplexer, allowing two different channels to be coexisting within this module. So the RX receive channel and the TX transmit channel are quite different from one another. So this is a diplexer. Now the other question is, what is the isolation between the RX and TX? Now we have to change the setup again in order to do that. So we're going to do the same thing. We're going to go under this trace. We're going to freeze this trace, and we're going to create a trace 3 now. And this trace 3 is going to obviously overlap the old trace again. Now I'm going to go change the setup, and we can see the isolation between the two channels.
And finally, the TX-RX isolation can be measured by connecting the tracking generator directly to the TX port and taking the RX port and connecting it to the receiver. And this is a really important parameter here because you want to make sure that the transmitter doesn't leak into the receiver. Now, normally you want to do this with an exceptionally high dynamic range, but we're going to be limited here by the instrument, but nonetheless, we can see if there is any relationship between those two ports.
All right, let's go ahead and run this again. Now we're going to see the isolation. So far so good. And check it out. It's pretty good. I mean, it has a little bit of isolation issue over here, obviously, but as you can see, it's doing a very good job. I can reduce the resolution bandwidth even further. Let's see how slow that would be. Let's see if I can do 0.5 kilohertz. No, it doesn't. No, I cannot go smaller. Never mind. I can't go smaller than 1 kilohertz. So this is the lowest we can go. But I can increase the number of points. Now, this is going to disturb my calibration, but nonetheless, let's double the number of points. We get a slightly smaller resolution steps there. And let's see what happens when it hits this region. Obviously, you're going to have to recalibrate this once you do this, but for our purposes, it's okay. There we go. So there's definitely some activity going on very close to the transitional point between these. And that makes sense, right? During the overlap region is the most difficult part, and it seems to be doing just fine. And normally this overlap region has guard bands and so on associated with it. But it's a very nice symmetric response. So you can see that how from the same instrument, same software, you can do all these measurements at once. Now, one thing this tracking generator doesn't have, or at least I couldn't figure out how to do, is that you cannot set the tracking generator step to 0. So you can't do a 0 span. Now, normally a 0 span is useful because that would allow you to use your tracking generator as a standalone synthesizer when you don't have it in any circuit like this. But I cannot figure out how to do this. I don't think it's capable of doing that. So if I go under span and I enter 0, it goes to 1 kilohertz. So that's the lowest span I can have, which means that the synthesizer coming out is going to jump back and forth within a 1 kilohertz deviation, making it a little bit less useful as a standalone synthesizer. So I think this is something that can easily be changed. If they want to use this as a standalone synthesizer, they should be able to do that. And I hope that they make this change as well, because it would be pretty useful.
So one of the great advantages of this instrument with regards to its tracking generator is that it can measure return loss and distance to failure as well as VSWR without needing any external coupler. So you only need this one port to do this measurement. And you can calibrate this port like you would do with a one-port network analyzer. It's going to do a scalar measurement, but you can do a short open and a load, and then you can do all of your return loss measurements directly from this port with no other component, which is fantastic. This is already a huge advantage compared to the competitors that require the external coupler. It makes it a lot easier to use, especially in the battery-powered version, and that's obviously why they've done that, because you want to be able to use this on the field without having to use anything else. So let's go and take a look and see how that performs. And I'm interested in measuring my tunable microwave filter, and I want to see its return loss as a function of its sender frequency. So you obviously expect this return loss to line up with its sender frequency. So let's see how that performs. I've terminated one end of the filter, and the other end I'm going to connect directly to this, and we should be able to do our measurement. But first we have to, of course, configure the software, do our calibration, and make sure that it is up and running.
All right, let's prepare the software. So let's go ahead and get the right window from the return loss window here. So we can do cable loss or return loss or distance to failure measurements. Now I'm not going to go through every single thing for the interest of time, but I recommend that you look at this. For our purposes, let's look at the return loss. Let me get rid of the spectrum. But the cable loss is also extremely useful. By looking at the loss of the return signal, you can compute the loss of the cable and so on. I'm going to leave that for some other time. So let's go ahead and take a look and see what this window looks like. Now for return loss and distance to failure measurement, you obviously need to do calibration in order to be able to create a reference plane at the edge of the cable you want to measure. So let's change the frequency. Let's look at a wider frequency. Let's go from 1 gig and all the way to, let's say, 4 gigahertz down. Let's increase the number of points to 501. So this is our setting. You can see right now I am connected to an open basically, and it's uncalibrated, so you're getting essentially almost 0 dB for the return loss measurement. Let's go and calibrate here. Now for the calibration, you can use the factory calibration or the user calibration. Let's do a new user calibration there. All the settings are already here. The cal kit parameters can all be entered, so it's a full-fledged calibration. It's not, there's no shortcuts here, but I'm not going to enter these parameters here because first of all, I don't know exactly what they are for my calibration kit, and for our purposes, we really don't need to worry about that. So let's do an open calibration here. I already have an open connected, so it's going to go measure that similarly like as you would with the network analyzer, except it's doing scalar measurements there. Let's go ahead and now do a short. And for a short, we're going to do exactly the same thing and do a measurement. There we go, connected, and a short measurement there. So now we're going to see that as well. And as soon as it's finished, I'm going to do a load calibration. Here we go. There is our 50 ohm. No, that's not a load. There is our 50 ohm load right here. And you can already see that we see the classic response over there. We're going to measure that. And it's going to look good once it's done. There it is. There is our calibration. Now it's applied and it's sitting below -40 because I'm turning it into a load. So if I go, let's say -80, I should be able to see it. There it is. So we are sitting really low, below -62 dB return loss. So we have a pretty good calibration. So let's go and disconnect that. As soon as I disconnect the load, we're going to jump right back up there, and I'm going to connect it to my filter. There it is. I'm going to set the filter to 2.5 gigahertz and check it out. So our return loss is right around here, and then as soon as we hit, and this is a little bit misleading, I should put that at 10 so that you can see the zero line because it was sitting at 9 dB per division. There it is. So we hit this right over here. This is the center frequency of the filter. You can see how well matched it is. It goes all the way down to -30, and outside it's back all the way up back to 0 dB, and there's a little bit of a ripple here. So if I put a marker, it's going to put it to the peak. It should also have a marker to minimum. There we go. There it is. So we can see our center frequency right now. We are sitting at 2.518 gigahertz. There it is. So this is correct. I can change the center frequency. It's running in the background. So let's go all the way to a little bit higher frequency. Now it's sweeping. I can't tell where it is. There it is. So it would be nice if it had a little point that showed you where the sweep was actually taking place, so you could see it. There you go. I just moved it forward. I can go all the way down to below 2.5 gigahertz. So on the next sweep, I should catch that. There it is. There we go. So you can see that you would be able to follow it if it was doing a little bit better job at drawing it. But yeah, so you can see how easy it works. And there's actually another window you can take a look at. So if I go under here, you can configure your distance to failure measurements, put all the parameters in there, and then you find out where the cable is failed. Now, this sitting at a bench, it may not seem very useful, but for the battery-powered version of this instrument, when you're outside in the field, then this is very, very handy. And you can change the displays. You can display the return loss or distance to failure. You can do VSWR. It's a full-fledged software. I can see that it is still being developed because some of the little features are still being added, which is great. And some of the comments I made earlier are the ones that I'm hoping they would add to this. And these are small changes that will make a big difference in the way the user is able to take advantage of this, especially the ability to do zero span, to be able to use the generator as a synthesizer. I mean, this is a 7.5 gigahertz synthesizer at your desk you would want to be able to use, and it makes this instrument much more useful. Yeah, so I think this should be a pretty interesting tool as well.
And there you have it, the full review of the Tektronix RSA607A that I hope you enjoyed. This is a really competitive instrument, especially at this price point. I cannot think of anything else on the market right now that can do as much as this at this price. So I definitely encourage that you take a look and see if it works for you and if it fits in your workflow. Now, there are several ways you can support my channel. First, you can, of course, leave a comment, subscribe to it, give it a thumbs up, and that way the video will have reach a larger audience. The other way is to support my Patreon channel, and the people who have been supporting my Patreon channel have been amazing. Because of their support, I'm able to, upgrade my camera. I have new audio equipment, and I'm also able to purchase new equipment from eBay to do more repair videos, which is something that I know you guys really, really enjoy. The other way you can help me is to contact the manufacturers and let them know that you enjoy these reviews or that they're partially responsible for you deciding to buy one of their equipment. I get no funds or no money from the sale of these instruments, but it helps me to have a good relationship with them and to be able to bring you state-of-the-art instruments as they come onto the market and review them for you. So I hope you enjoyed this, and I'll see you in the comment section.